Hey guys, how's it going? Hey, I was getting a little tired of sitting at my computer and updating the wiki and doing all that. Although I've enjoyed very much doing that, I figure I would give you a little lecture. And I like a little technology, so I thought I'd try something new for you today. So, again, for anybody who's watching, this is physical chemistry with quantum mechanics focus. So it's actually physical chemistry 2, and we are at Monmouth College. Well, I'm at Monmouth College. You are spread out around the great state of Illinois, as well as surrounding states and even further away. So we just finished chapter 9. Okay, chapter 9 talked about the hydrogen atom. And one of the things that was so great about the hydrogen atom, it kind of pulled together all the stuff that we worked on all throughout the semester. So again, in the hydrogen atom, you have a positive charge in the middle. You have that electron on the outside. The electron is moving around. There's kinetic energy associated with that. And then there's a potential energy, which is a Coulombic attraction between the electron and the proton that sets up the energy aspects of this system here, the hydrogen atom. So like we've done throughout the semester, we're looking at Hamiltonians. We use Hamiltonians in the Schrodinger equation. We solve the Schrodinger equation, and by doing so we get the wave functions, but we also get the energy or the eigenvalue resulting. So in this particular case, if we think about it as the potential energy, we talk about that electron moving. That's the minus h bar squared over 2 times the mass of that electron. And then we can use a shortcut and just do del squared. In last lecture, I showed you some of these. I did some screenshots from some other physical chemists who had the del squared in both Cartesian coordinates and spherical polar coordinates. So the kinetic energy part for this one is, again, oftentimes we add these two together. But when we talk about the Coulombic attraction here, we're talking about the charge on the electron and the charge on the proton. They are the same charge, but they're opposite in sign. So there's the minus from the electron, there's the E from the electron, and then here's the squared to give you the charge of the proton. That's divided by 4 pi epsilon naught times r, which is the distance between those two. Okay, now this is the Hamiltonian. What I might suggest that you do now is just pause the video and write out the complete Schrodinger equation. And if you really want to review this, you could go ahead and write out the del squared. I would say go ahead and just do it in spherical polar coordinates. There are Cartesian coordinates that you could write out there, but those aren't necessarily as useful when we think about solving for the Schrodinger equation. The wave function, r of r theta and phi. Sometimes we just use the big wave function on there with n, l, and m sub l, those quantum numbers associated with that wave function. Did you pause? Did you write out that Schrodinger equation? I think it might be a good idea to do so. All right, so again, we need to move on now to chapter 10. And now chapter 10 this is a multi-electron systems. So in a multi-electron system, probably the easiest one to talk about is helium, right? So in helium, you've got a 2 plus charge here in the center. You've got 1 electron out here that now we should probably put a subscript on there. And then we have another electron, E2, down here. Now this electron is moving around, and this one is moving around. There is a Coulombic attraction between here and here, and there's a Coulombic attraction between here and here. So if we focus first on electron 1, so electron 1, there's a minus h bar squared over 2me1, but since electrons all have the same mass, you could probably leave that off. And we could do del squared again, but in this case, let's label it as E1 because this is the potential energy term associated with electron 1. Now with electron 2, we now have to have a second term like this, mass of the electron, and we have now del E2 squared. So now we've got the kinetic energy terms for electron 1 and kinetic energy term for electron 2. And now we have to look at the Coulombic attractions because this is now the potential energy term. Actually, it's not much different than what we had in the hydrogen atom. So we have that minus electron, we have the charge in the middle, but now this is 2e. So if I do 2e, let me just rewrite that for you here, minus 2e squared, right? Where that 2 essentially comes from the fact that this is a 2 plus charge in the center. Okay, it's also divided by 4 pi epsilon naught, permeability of space. And now in this case, we're talking about R1 and the proton. So let's just call that R1 up here in our diagram. Now we need to add to that another term, and this is the second one down here, right? This is the potential energy term for electron 1. This is for 1, this is for 2. And then here we have the same thing. Again, you've got the negative charge of the electron, the positive charge of the proton. So you end up with a minus 2e squared again. And now this is 4 pi epsilon naught r now 2, where we call this one R2, which is essentially the distance of the electron 2 from the nucleus. Now what makes this system much more difficult and ultimately is the demise of a multi-electron system is that these two electrons now know that each other are around. So the form of that potential energy, again let me write that in here, potential energy for 2, is the same Coulombic attraction, but now it's between 2 electrons. So now we're going to add, you've got a negative E and a negative E. So now you have a positive E squared over 4 pi epsilon naught. And now we need to define this as R12. Note when we have 2 subscripts on there, it's between electrons. And when you have 1 subscript in there, it's between the proton and that electron. So now we have an R12. This, or these, are the terms in the Hamiltonian for the 2 electron system, and you can see that this is a bit more involved. If you went out and you wrote out the Schrodinger equation for this, you would find that the wave functions or the solutions to this are going to be significantly more involved. Again, I just point out the fact that these wave functions are mathematically complex, not only because they have an I in there, but they're complex in nature, meaning you have lots of terms. But that doesn't necessarily make them difficult. They're just complex. There's a lot to them. Actually, so here's what I want you to do. Now, I'm going to erase all this stuff here. And I want you to now write out the Hamiltonian components associated with something like lithium. So a lithium molecule, right? So here, I'll draw it right here in the middle. So lithium is a 3+, and there are 3 electrons. So there's electron 1, there's electron 2, and there's electron 3. So now you're going to have, under our kinetic energy terms over here and our potential energy terms, you're going to have under the kinetic energy here, the E1 kinetic energy. We're going to have an E2 term. We're going to have an E3 term. So each one of those are going to have a separate kinetic energy with the del squared function in there. Now potential energy terms, we're going to have this one right here, which would be R1. This one right here would be R2. And this would be R3. So under potential energy, note we got a 3 charge. There's going to be a minus 3e squared. and then there's going to be a 4 pi epsilon naught R1, 2, or sorry, R1, this R1 right here, that potential energy. So you're going to have another term that has an R2 in it. You're going to have another one that has an R3 in it. Now, when it comes to the other potential energy terms, we're going to have this one. This would be R12. This one would be R23. And this one right here would be R13. So now you're going to have an R12, R13, R123. So you're going to essentially have 1, 2, 3, 4, 5, 6, 7, 8, 9 different terms for the lithium atom. And again, you could write this all out. I suggest that you do that now. All right, so I want to focus just on the Hamiltonian today. And when we get together on Friday, we'll talk about the wave functions. Because again, you can see, hopefully from the notes that you've written out, that these Hamiltonians and the overall Schrodinger equation are really, really quite complex. When it comes to solving for these multi or the electron-electron interactions, this is really what prevents us from being able to solve the Schrodinger equation. And so what we're going to have to do is we're going to have to start making approximations about how everything is essentially going to work out. So those wave function approximations are the next step in our conversation. So I hope you enjoyed today's lecture. I am Brad, or sometimes I might be referred to as Brad, or sometimes even B-Rad. Have a good day.